A very good morning to all of you, and I hope everybody is fine, everybody is doing fine. And the target of this video is basically to introduce you with indistinguishability of the identical particles. And let us have an introduction of what we mean by indistinguishability in the framework of quantum mechanics, and then give an idea of exchange interaction. This exchange interaction is a very strong mathematical tool that guides us to understand some of the complex systems. So, so this presentation will basically lead us to simply introduce you with what we call as indistinguishability of the identical particles. So to run with, what I attribute is the interaction here, what quantum particles are. We know we have quantum mechanical particles like electrons, protons, atoms, molecules, and these particles can be identical. They can be of same nature. What identical means, we will come to that slide, but we can attribute the identical nature of these particles like electrons, protons. So what identical particles are? They are indistinguishable in the framework of quantum mechanics, and this is what leads us to the unique statistical behavior of the complex systems of these quantum mechanical particles. So what are the identical particles? How we can say that the two particles are identical? I mean, what are the basic identification marks for the two particles to be identical to each other? Is that identical particles have the same intrinsic properties. I mean, they must have the same mass, they must have the same charge, and they must have the same spin. There can be some additional terms also involved in it, but these are the basic properties that these particles must have identical. So if they are identical in terms of these physical quantities, then we call them identical particles. So they cannot be distinguished in principle, which is basically contradictory to the classical world, where you can have the identical particles, but at the same time you can distinguish the particles in the classical domain. And we can have examples of distinguishability that we have in the framework of classical physics. So we'll be talking about that. So what we have here is classical versus quantum. So in classical mechanics, what we have the particles, and these particles are always distinguishable, even if they are identical. So if you have two identical classical particles, they have to be distinguishable. But in the framework of quantum mechanics, identical particles must be treated differently. You cannot exactly treat these quantum mechanical particles the way you treat them in classical domain. Now, talking about this indistinguishability principle in the framework of the wave function. As we know, the basic tool of quantum world is the wave function. The overall information about the system is enclosed within that wave function. But at the same time, this wave function does not have any physical implications unless you calculate its probability density. So trying to understand this indistinguishability principle, what we have, the total wave function of the system must reflect this indistinguishability. It is the total wave function that defines your system. And this total wave function, this energy eigenstate, leads us to learn about the indistinguishability of these identical particles. So swapping the two particles should not produce a new physical state. So what we have, if there is swapping of the particles in your system, it should not lead us to a new state. This is what a new physical state. So if it doesn't, it certainly must have some implications. Now, symmetric and anti-symmetric states. Now we have that wave function, and this wave function gives us the information about our system. Now what happens if I have a wave function, say for example, phi of x1 and x2, and assuming that x1 and x2 are the probabilistic positions of the particles within the framework of this wave function. Now if you exchange the two identical particles, the exchange gives you the same wave function, then such a wave function is termed as symmetric wave function. And this is the framework that falls in the context of bosons, what we understand as the systems that obey the Bose-Einstein statistics. And if we have a system, if our wave function changes the sign by interchanging the particles enclosed by this wave function, then we call our wave function as anti-symmetric wave function. So we have symmetric wave function. By exchanging the particles does not change the sign of our wave function, but at the same time, in the framework of bosons, if you exchange the particles, what you calculate finally is the sign change in the wave function. So this sign change leads us to the anti-symmetric wave function, and fermions are examples of following the anti-symmetric wave function, following the Pauli's exclusion principle. So certainly Pauli's exclusion principle, what it does, it applies to fermions only. It does not apply to bosons, where on exchanging these identical particles, the sign of the wave function does not change. And what it means no two fermions can occupy the same quantum state. Because when you exchange the particles in your eigenfunction, you come up with an eigenfunction with the same eigenfunction but with a negative sign, leading us to a conclusion that two fermions cannot occupy the same quantum state. So certainly helps us to explain the electronic structure in the atoms. Now, talking about the exchange interaction, what we have is quantum effect due to wave function symmetry. So when you have an interaction, this interaction has an exchange. So this exchange can be identified using the symmetry of the wave function. As I said before, that this exchange can lead us to bosons, and this exchange can lead us to fermions. So what's happening here? It leads to the effective interaction without any physical force. So when you exchange, when the wave function you have, when you exchange the particles, the calculation of the wave function leads us to an effective interaction without any physical force acting on that system. And this is very important in understanding the very quantum mechanical behavior of solids, where what we call magnetism and the bonding in the solids. So exchange energy. So what we have, difference in energy due to exchange. So once you have exchange of the particles, this exchange takes our quantum system to a new energy state. So by calculating this exchange interaction, we can basically calculate this difference in energy due to the exchange symmetry. And this is what contributes to the stability in molecular and solid state systems. Now, let's talk about the fermionic exchange. So, fermions, say for example electrons, if you exchange the two electrons, so what it leads us? It leads us to the negative value of the eigenfunction. So, negative sign on the particle exchange causes the repulsion-like behavior. So this repulsion is also important for the balancing, for the stability of the system. You cannot have a one-way process, or it's all say everything all about attraction. It's going to collapse everything. So what's happening here is calculating this exchange, leading us to the negative value of the wave function, leads us to understand the repulsive-like behavior between these fermionic particles. And they are responsible, it is this behavior, it's this negative sign that we calculate by exchanging these fermions. This thing is responsible for the stability of the matter, as I was talking about. Now, if you exchange the boson, what we call as bosonic exchange, what you have the positive sign, you have exchange of the two bosons. This positive sign of the particle exchange allows the multiple occupancies in the same quantum state. So this is what leads to the phenomenon like what's called as Bose-Einstein condensation, and for which people have achieved the Nobel Prize. So if the sign of your wave function does not change, you're basically talking about the bosonic exchange of your systems. Now these exchanges, what we have, they have the applications in electron configuration, magnetism, and superconductivity. Talking about Bose-Einstein condensate and laser physics, in solid state physics, and in quantum chemistry. These are some of the important applications of these quantum mechanical indistinguishable particles. So the point is, in classical domain, suppose I have a particle 1, I have a particle 2, and these two particles move. Say this is the position 1, and this is the particle 2. This is position A and this is position B. And I allow these particles to move. Now, if these particles are moving, I can distinguish them classically, reaching out to the destination. Suppose this is C and this is D. I'll say that the particle A has reached to C and particle B has reached to D. And the reverse is also true. Now, what is happening here? Here in classical domain, you are able to check the trajectory of the particles. So since you can go with the trajectory of the particles, that means you can exactly distinguish two particles, say particle 1 and particle 2. So that's why in classical world what we have identical particles, but these identical particles are distinguishable particles. But that's not the case when it comes into the framework of quantum mechanical particles. So you cannot distinguish one electron from another electron, electron 1 and electron 2. You cannot distinguish between the two electrons. Why we cannot distinguish? The reasons should be that in quantum mechanics, we don't have trajectories. So if you don't have trajectories, you cannot distinguish which particle has reached to the position C and which particle has reached to the position D. I think this is the basic plausible explanation of having indistinguishability of the quantum mechanical particles and distinguishability of the classical particles. So to conclude this introduction, what indistinguishability leads? It leads to the fundamental quantum behavior of the system. So exchange interaction has real physical implications, it has real physical consequences, and both these things are very important. They are very crucial for understanding these quantum complex systems. So with this, I would like to stop here, and I hope you like it. If you like it, I request you to share this video among your friends.